Now next derivation is force exerted by a jet of water on a series of vane. Means here in the figure you can see a wheel is given, and on that wheel various plates are being mounted. So we have to find out the force acting on this wheel on which these plates are mounted. And here you can see in the figure a nozzle is there through which a jet is coming out of. V is nothing but velocity of jet, D is the diameter of the jet, A is the cross sectional area of the jet, and the velocity of vane is nothing but U. Velocity of vane we are considering because after jet is striking, the plates will start moving, so there will be certain velocity for that movement, that is nothing but U. Now first of all, mass of water per second striking the series of plate is rho into area into velocity V. Now here jet strikes with the velocity, that is V minus U. So therefore velocity component in the direction of the plate is 0. So therefore your Fx will be rho into area into velocity initial minus final velocity. Initial velocity is V minus U, final velocity is 0. So therefore Fx is rho into area into V in the bracket V minus U. Next you have to find out the work done per second by the jet on the series of plate, that is Fx into U. So therefore W will be rho into area into V in the bracket V minus U into U. Unit is Newton meter per second. Now here you have to find out the efficiency of the jet. So for finding out that efficiency, you must know the kinetic energy per second of the jet, that is half mv square. Half m is nothing but rho into area into velocity V into V square, that is half into rho into A into V square. Efficiency is output divided by input. Output is nothing but work done per second on the series of plate divided by kinetic energy per second of the jet. So therefore efficiency is equal to 2 into U in the bracket V minus U divided by V square. Now efficiency, if maximum efficiency occurs when your V is equal to 2U or U is equal to V by 2. If this condition is there, then you can obtain maximum efficiency, and maximum efficiency is your 50%. Thus this was the derivation for the series of vanes. Now next derivation is for force exerted on a series of radial curved vanes. Now here in the figure you can see a series of radial curved vanes which are mounted on the wheels. Now here radius at inlet and outlet vane are different, so the velocities will be also different. Radius are different, so velocities will be different. As you can see in the figure, here R1 is the radius of wheel at the inlet of the vane, R2 is radius of wheel at the outlet of the vane, and W, that is angular speed of the wheel, that is as omega. So therefore U1 will be omega R1 and U2 will be omega R2. Again what you have to do, velocity triangles at inlet and outlet you have to draw as shown in the previous slide. Now here mass of water per second striking for series of vane, that is rho into area into V1. Now momentum of water striking the vanes in the tangential direction per second at inlet is given as mass into component of velocity in the tangential direction. So therefore rho into area into V1 into VW1. Now here your V1 cos theta is nothing but your VW1. Similarly moment of water at outlet per second will be again mass into component velocity in the tangential direction. So rho into area into V1 in the bracket minus V2 cos of beta. At outlet angle is beta. Negative sign due to the opposite direction. Now you have to find out angular momentum per second at the inlet. Angular momentum is nothing but the momentum at inlet into radius at inlet, that is rho into area into V1 into VW1 into R1. And similarly angular momentum per second at outlet is nothing but negative rho into area into V1 into VW2 into R2. Now next you have to find out torque. Torque exerted by the water on the wheel. So torque is given as rate of change of angular momentum. So T is nothing but your angular momentum per second at inlet minus angular momentum per second at the outlet. So therefore T is nothing but rho into A into V1 in the bracket VW1 R1 plus V2 R2. Now next you have to find out work done per second on the wheel. So here work done can be found out as into torque into omega, that is angular speed. So that is rho into area into V1 in the bracket VW1 U1 plus VW2 U2. Now here if angle beta is obtuse, then work done can be given as rho into area into V1 in the bracket VW1 U1 minus VW2 U2. And if beta is 90 degree, then W can be given as rho into area into V1 in the bracket VW1 U1. These were for the work done. Now efficiency again, output upon input. Output is nothing but work done per second divided by kinetic energy per second. So therefore you can obtain efficiency as 1 minus V2 square divided by V1 square. So that's it. These are all the derivations required for the impact of jet. Thank you.